can we get started? So today we have a special guest speaker, Professor Hashimoto from Johnson University. He's a world famous expert on FRB. Then today, he's going to tell us about cosmology using fast radio bursts. And then, we got the class funding to invite the guest speaker. Then he came to just for us. First of all, thank you very much for coming. And then,
yes.
Please take advantage of this opportunity. Maybe, at the end of the class, you can, please feel free to ask questions to Tetsuya-san.
Sure.
And also, at the end of the class, maybe we can have some time to ask, to chat with the speaker. Something like, something you guys are interested in, how do you find a job after graduating, or what would be useful, or something like that. Okay. Yeah. So please think about what you want to ask. You can ask something like that. How much is the salary of astronomer? How much of the salary of professor? Do you know how much is the salary you are interested in?
Sure, if you want. Sure.
You can ask. Okay, so
yes.
I should stop speaking. So let's welcome Professor Tetsuya.
Okay. Okay, thank you very much for this opportunity, and thank you very much for very good introduction. So as Tomo-san already introduced, so I am Tetsuya Hashimoto from National Johnson University. I think all of us are Taiwanese students, I guess. But anyway, so I will explain a little bit about myself later, just for my introduction. So this is my Chinese character. So Chaopan Jaiye is my name. So in Japanese, Tetsuya Hashimoto. So nice to meet you. And thank you very much for your time today. Today I'm going to talk about this fast radio burst. So that is getting popular recently. So let me emphasize this kind of things first. And then today, mainly in my talk, I include these two papers recently written by our research groups. I just take a picture from our press release this year. This was given by Shotaro Yamasaki, Shotaro-san. So I will explain this one later. And also, I have many opportunity to work with Tomo-san, famous professor over there. So I just put a picture taken with him. So this was taken in Japan. So in Japan, they have many radio telescopes. So we visited one of them, this in Ibaraki University just before. Okay, so let me get started. So therefore, as Tomo-san mentioned, so I think please feel free to stop me when you have any question. So please be relaxed. So you can ask anything. So there's no stupid question in this class. So please ask me if you don't understand what I'm saying. Just in case. I may expect you guys are maybe future researchers in astronomy. So therefore I really want to advertise our university as much as possible. So, Johnson Dash, right, the National Johnson University is in Taichung City. So, I am doing astronomy in this university. So, they have a department of physics. And then I am a teacher at the department of physics. And then, physics can include astronomy. So, therefore, this is one of the places that you can learn astronomy in Taiwan. So, future, if you have a chance, please visit us. It's like this. Taichung City, I think it's good to stay, I believe. Just for my advertisement, so I have a research group working on astronomy. I'm not sure if you know about this. Postdoc is they are working on astronomy as a job. So they get paid by doing research. So we have 3 postdocs who are working on fast radio burst. and then also 4 PhD students, 2 masters, 2 undergrads, and then some external students that I'm working with. So this is a kind of size of our Astro group at NTHU, National Joshi University. So I hope you guys have a chance to visit someday in future. This is actually all thanks to Professor Tomo-san. So I was actually postdoc in National Tsinghua University here. I was really working here for 4 years or so as a postdoc. And then fortunately, I got a teacher's position at the university, Joshi University. So I'm so happy to be here today. So thank you very much. And then this is an outline of my talk today. So let me try to introduce this first radio burst. What is a heartbeat? So I think this is the most important part in today's lecture. I don't really want to go to difficult things. I try to explain as easy as possible. So I don't really go to details. And then this is a cosmology class, I think. So therefore, I try to include cosmology, topics in cosmology. So let me discuss cosmological proofs FRBs for cosmological proofs. And then I will include 2 topics here. One is baryonic distribution in the universe, and then second one is cosmic expansion. So I will really explain how it works using first radio burst. And then in the remaining time, actually this FRB science is really getting popular in Taiwan. This is because in Taiwan, so we are building new radio telescope, which is dedicated to finding FRBs. So I will explain this one. This is burst project. Okay, later if I have time. Okay, so I start, but I think I start slowly. So this is usually I show for introduction, and this kind of schematic video. Reality is really, thank you, Tomo-san. Thank you very much. So, you know, in astronomy, we can use different types of telescopes, right? So with our eyes, we can see the sky in optical wavelengths. But we can use radio telescope to see the universe in radio. That's also possible, right? And then this video is highlighting how they look different. Say this optical is okay, right? So we are used to see the optical sky because we can see it with our eyes. But we can see the sky using radio telescope. And then that looks very different from optical view. Maybe you can find the difference. But significant difference, you see this Milky Way line here, and also something huge structure on sky in radio. But this time, I'd like to emphasize the most significant difference is the flashing object. So now, people in astronomy, they notice that there are so many new flashing objects in the universe that no one noticed before. This is happening in radio. It's not optical. Optical, we don't see this flash. But in radio, there are so many radio fireworks are happening somehow. Then this is called the first radio burst in my talk. And the problem is we don't know what they are. So that is getting one of the outstanding questions in astronomy now. So let me explain this. This is just for imagination. This is not a real, flashing object is artificially injected in this video. Because this flash is only 1 millisecond. I will explain this one, 1 millisecond. If I put it in video, I cannot see it actually. The flashing is actually artificial. But anyway, to get a better understanding of this, I put a schematic diagram here again. So what is first radio burst? So this is very short radio pulse, which are coming from galaxies in distant universe. And then, interesting point is, this flash is only millisecond. So only millisecond. Millisecond means this is 1,000 times shorter than 1 second. And then typical time scale, say in our daily life, say 1 millisecond is, say like a thunder, say thunderlight. Thunderlight is say about typically 1 millisecond. It's really a moment of flash. But this is happening in radio somehow. And they are very bright in astronomy. Therefore, even they happen in distant universe, so they can reach our Earth, then we can detect it. So this is schematic diagram. So there is a galaxy here, and then in this galaxy, there is an astrophysical source which is emitting this radio pulse or radio signal. And then this propagates from this galaxy to all the way to this telescope on our Earth. Then we can detect it. And then these things, this is a schematic view of FRB signal. Okay. So we are receiving the signal from the sky in radio. So far, there are so many FRBs already detected. Number of detected FRBs are more than 500 FRBs. But with 500 FRBs are detected by looking at only tiny region of the sky. So if we expand this number to the whole sky, there are more than 1,000 FRBs are happening every day. 1,000 FRBs are more than 1,000 are happening every day. So this is so many compared with other astrophysical sources. So therefore, people really want to understand what they are, but it's unknown. So that's a problem. We won't understand. This is just advertisement. I'm sorry. This is just advertisement. So I'm starting slowly. I just want to emphasize that FRB science is getting popular. Okay. There's a famous professor here, Tomo-san. So this is Shotaro. He's a researcher in my university. We are working together. So this is me. So our paper, actually Shotaro's paper, so we are working together. Shotaro's paper was selected for press release in Japan. So therefore we did it, press release. And then our paper show up in news in Japan. This is, you can see Japanese. So it was shown in Japanese news. That's good. So then we just wanted to do the same in Taiwan too. and then Tomo-san again. So I want to emphasize FRB is getting popular. So they really want to feature these kind of things. Then we also did this press release in Taiwan, actually in Johnson University. This is Tomo-san, right? I can emphasize Jimmy is your senior. So he was a student at NTHU, then he just graduated and he moved to Japan now as a PhD student. But he's your alumni, right? One of our alumni at NTHU. So I'm really proud of this, having Taiwanese students and Japanese collaboration here. And then many news articles in Taiwan, they featured our work. So then I also like this, this one, because our paper here, shown here, I don't go to details, but it's above Otani here. I don't know if you like Otani. Otani is the most famous baseball player, so then our news articles, more than Otani. So this is showing how popular FRB is now, okay, in society, okay? Please try to understand what I'm saying. Then this is Taiwan and Japan, right? But it's not only Taiwan and Japan. This is worldwide now. Actually, if I look at the past prize, this is one of the most famous prizes in astronomy over the world. And Shaw Prize, and there are many people who get Nobel Prize after getting Shaw Prize. So therefore, for some case, people may say this is a future Nobel Prize. So then, and this Shaw Prize in 2023 was awarded for FRB science. So there are 3 professors, One of them, he is the first author of first discovery of FRB, Duncan Lorimer. He is Marshall Bells, Australia. He's actually going to visit us, Taiwan, next month. So Taiwan, we have international conference next month, so then he will come to Taiwan. Future Nobel Award. But anyway, so FRB is really recognized, not only in Taiwan, not only Japan, it's worldwide. Okay, very famous now, very popular. Then I want to explain why this is getting popular in astronomy. So I would say first radio burst, FRB is kind of special. This is special, maybe different from other astrological sources. This is because people expect using first radio burst, we can address the most important issues in physics or in astrophysics, including, say, missing baryon problem that I'm going to talk about later. So this is one of the biggest issues in astronomy. So FRBs are very useful to address this problem. Testing general relativity. So yes, of course, testing general relativity, this is always important, right? Say, discovery of general relativity was made by accurate measurement of speed of light. FRB allows us to measure the speed of light very accurately, so that's maybe useful to test the general relativity, okay? To find something new theory beyond general relativity. I don't have time, I'm sorry, to talk about this one. Cosmic expansion, this is astrophysically very important, right? So Hubble constant, or cosmic expansion rate of the universe. This tells you the size of the universe, right, or age of the universe. So this is one of the most fundamental quantity to describe the universe. So if you are in astronomy, you should pay attention to Hubble constant, okay? This is the most important parameter that we want to derive astronomy. But somehow, I will explain this one later. Somehow, different method to derive Hubble constant gives you different answers. So this is a problem, so-called Hubble tension. I will explain this later. But FRB is useful for this one. And then also, I'm not sure, maybe Tomo-san already introduced this cosmic reionization. Maybe no, okay. This is kind of related to the history of the universe. So the universe has a very long history, starting from neutral phase. Then currently our universe is on average ionized. So therefore there should be certain time that the universe is ionized on average. This is called so-called cosmic reionization. So this is supposed to be closely related to the first formation of stars or first formation of galaxies. So therefore people really want to understand cosmic reionization history. This is a cutting edge of galactic astronomy now. So then FRBs are supposed to be also useful for this, but I'm sorry I don't have time to talk about this one probably. If I have a chance, I will talk about this. Dark matter, maybe I don't need to explain this one, but this is another biggest mystery in astronomy, right? Dark matter. Anyone in astronomy, they want to understand what dark matter is. So FRBs might be useful to address this dark matter too. So there are so useful applications of FRBs in astronomy. So people expect. So therefore, before we can use FRBs as a useful tool in the universe, so we really need to understand what they are. So therefore, I put this one too. So understanding origin of FRBs is getting more important recently because this is supposed to be very useful to address other big problems in astronomy. Then why can we do this using FRBs? Why not other sources? Let me explain this. So this is really saying why FRBs are special in astronomy. So I'm getting a little bit more details now. Please stop me if you have questions. I think I should measure time, right? I'm speaking too slow. And this is luminosity. So how bright are they? They are. So how bright it is, right? Astrophysical source. As a function of duration. So for example, pulsars is emitting, say, radio with specific period. So this is a very short time. So 10 to the minus 3 seconds means 1 millisecond pulsar time scale. And then say other sources, for example, gamma ray burst, GRB. So this is a gamma ray burst. This is a very most energetic explosion in gamma ray. So they are very bright. Okay, explosion energy is very high. They are very bright, and the time scale is long actually in this diagram. Or AGN is active galactic nuclei, so supermassive black hole. So they are also bright. So we can detect these bright objects at distant universe. And then, where is FRBs? FRBs are here. So they are actually in this unit of luminosity. FRBs are as bright as other populations. So brightest populations in the universe. Okay, gamma ray burst, AGNs. Okay. So therefore, basically, this figure is saying that FRBs are very bright, so we should be able to detect them at a distant universe. That's good. But time scale is very different. Okay. We can detect FRBs at a distant universe. But difference from these guys is time scale, many orders of magnitude shorter. And this is comparable to the pulsars. Extremely bright, but time is extremely short. Say 10 to the minus 3 seconds, 1 millisecond. Okay. So this makes FRB special in astronomy. Because in this parameter space, there is no other astrophysical source which can explore this parameter space, very bright and short time scale. There is no other astrophysical source. No, only FRB can do this. And then this is important. A bright and short time scale. So this makes FRB special in astronomy. Then this will be super useful in astronomy. Then I try to explain this in next slides. Why this is useful in terms of cosmology. This is cosmology class. Let's say this is again schematic diagram. So we are in this galaxy. Say we have radio telescope here. And then there's a picture of the universe. And then this, you know, these bright spots, they are all galaxies. There are so many galaxies in the universe. But then, how about this empty space? The space between galaxies, it looks black. Is nothing empty? Or not? It looks empty. Yes, it looks like empty. It is dark, black. But actually, this intergalactic space is supposed to be filled with plasma. There are material between galaxies. They are diffuse plasma. So therefore, actually, it's not a complete vacuum between the galaxies, space between galaxies. Okay. And then please keep it in mind. And then let's say FRBs are happening at a very distant universe. Then this radio signal propagates from here to here. Then we can detect this FRB. And then in this light path, most of the time, this is propagating the space between galaxies. Okay, most of the time. But in this space between galaxies is not a perfect vacuum. Okay, there's a certain amount of plasma, diffuse plasma. So that means plasma physics comes here, but I don't want to say difficult things. According to plasma physics, when radio signal propagates inside the plasma, actually speed of light changes. So radio is one of the electromagnetic waves, right? So the speed of radio signal should have speed of light constant if it is in vacuum. Okay. But in reality, universe is not a perfect vacuum. So there is a plasma. So therefore, radio signal propagating inside the material. Therefore, when the signal propagates inside the material, the speed of light changes. Then we can see similar effect for prism. So this is optical light. Optical light is also electromagnetic waves, right? Propagating inside the material. And then speed of light change. Therefore, this has this refraction, right? So this is a prism. People call it dispersion effect. This is because speed of light changes inside the material. Then similar things happens for radio signal propagating in the universe. Then speed of light changes for FRB. Then FRB is happening in radio wavelengths. Then in radio, actually this radio includes high frequency radio and low frequency radio. Then according to plasma physics, a high frequency radio, this is not affected by plasma effect very much. This can keep original speed of light in the vacuum. So it goes fast. Speed of light is fast for high frequency part of FRB. But low frequency part of FRB is significantly affected, and the speed of light becomes slower. So therefore, FRB is happening here, and this is happening in radio. And this is emitting both high frequency and low frequency. Then even if they start at the same time here, propagation speed is different. Then arrival time is different for high frequency and low frequency. This can be shown in observed data. So this is observed data using telescope. Y-axis is observed frequency as a function time here. As you can see, there's a tilt line here. So this is a typical example of FRB detection. As I mentioned, high frequency go fast. That means it will arrive high frequency, say 1.5 gigahertz. It arrives earlier time, okay? Low frequency is slow. So therefore, low frequency, say 1.3 low frequency in radio, arrives later. So they have a time lag between high frequency and low frequency in arrival time. So this is very important. This is called dispersion measure. And then why this is important? Because now this can be used as distance indicator or indicator of baryons in the universe. Let me explain. Now, I hope you have understanding about this case, single FRB. That's fine. I hope that's fine. But I can imagine there are two FRBs here now. FRB 1, FRB 2, happening at different distances. Okay? Different distances. And then for FRB 1, there are more plasma between FRB 1 and then telescope. So then this makes longer time lag between high frequency and low frequency. But FRB 2, this happens in nearby universe. And then distance is short, right? Nearby universe. And the amount of plasma is also short. So that means amount of plasma is small. So that means time lag between high frequency and low frequency is short. Okay. So the situation is like this. When we find two different FRBs in data. So 1 to here, 2 lines. FRB 1, time lag is, let's say this is a long time lag. long time lag, okay, between this and this frequencies. This is long, right? Long time difference. Time lag large. But for this guy, for the same frequency range, the time lag is very short. Okay. So that means by looking at this data, so we detect FRB and then look at the data, then I can tell which is more distant. So this is more distant because you have more time lag. You have more time lag here. So therefore, just by looking at the FRB signal, so I can know that this is nearby because time lag is very short. This is saying we can use this tilt or dispersion measure as a distance indicator. So we can measure the distance in the universe using this time lag of FRBs. And this only FRB can do this one because you can see the typical time lag because of the plasma effect. This is, you can see millisecond time scale. So this plasma effect is typically, this happens millisecond time scale. So therefore, if you use longer time scale, say 1 second or 10 seconds or 1 minute or something, longer time scale, astrophysical source which has longer time scale cannot do this because this time lag caused by plasma is millisecond time scale. So only FRB can measure this dispersion measure. And there's no other astrophysical source that can do this. So therefore FRB is very special. So that's why many people started to pay attention to FRBs now. And then this can be used cosmology distances. And also more directly, this is measuring how much amount of plasma you have between FRB and the telescope. So therefore, amount of plasma is also can be measured using dispersion measure. So therefore, FRB's dispersion measure can be used for multiple purposes. At least, say, amount of plasmas in the universe or amount of baryons in the universe. And also, we can use this as indicator of cosmological distances. So that's why FRBs are closely related to cosmology. Okay. I think I'm spending too much time. Then I hope I think this is the most important part of my talk. So then other things I'm just going to details. But then if you are interested in FRBs, that's success of my lecture. Anyway, so then in the remaining time, I want to talk about some works by our research group and also Thompson's group. One is about the missing baryon problem. So, but I noticed that I think we should take break. No? Is that okay? It's to me. Then let's follow the regular lecture. I think we usually take 10 minutes break after 1 hour. So then, no, not yet. 1 hour not. Okay. We started 2:20. Okay. Then later, let's take 10 minutes break. Okay. Then I have a little bit more time. Then let me start this part. Missing baryon problem. How can we address using first retrievers? The missing baryon problem, I'm not sure if you learned about this one before, but this is a very famous problem in astronomy. The baryons are kind of ordinary material that we well know. For example, table or our body or in classroom or any entities made by, say, proton, a neutron, or something we know very well, right? So these materials are so-called baryons. We well know that their behavior. So then in the universe, so yes, we do have baryons. And then from cosmic microwave backgrounds or Big Bang nucleosynthesis model, so they can precisely measure the total amount of baryons in the universe. They can predict. So then different methods has very accurate agreements between different methods. So therefore, we will know the total amount of baryons. We have a very good measurement of total amount of baryons in the universe. Okay. We know this pie chart. Total amount, we know. Okay. But then on the other hand, we can count the amount of baryons in the universe, say one by one. For example, we can see galaxies here, right? Say in this picture. So we can see many galaxies here. So galaxies are basically including baryons. That's why we can see them. Okay. We can count how much galaxies there are in the universe, then counting baryons. Or we can observe gas, then how much baryon exists in the universe. There are multiple methods to measure baryons in the universe by using telescopes. So we can directly find baryons. Then we can accumulate, right? Different methods. And then they accumulate what we can find using telescopes. And the problem is they try to count as many as possible that is visible using telescopes. I mean amount of baryons. And then problem is what we can observe is not enough to explain the total amount of baryons. So there's always a significant portion of missing population here. So we know that total amount. Also, we can confirm how much baryons exist by counting how much baryons, okay, using telescopes. And then they don't agree each other. There's a missing part. We don't see enough baryons using telescopes. Okay. This has been a long-standing problem. And also, this is one of the most outstanding problems in astronomy. Many people really wanted to understand the baryon budget in the universe. So somehow it doesn't agree. But one expectation was, okay, missing baryons. But people expect probably this missing part is hard to find using telescope because they are not emitting radiation. So in astronomy, we have to find radiation, right, from material. Then we can find that they exist. But if there are plasma, diffuse plasma in intergalactic space, this diffuse plasma doesn't emit the radiation very much. This is the reason why we can see dark here. Using telescope, we don't see anything. This is the reason why it is dark. But people expect there should be plasma here. We cannot see that using telescope, but they should exist. But observationally, there was no evidence of this so far before FRB. That's why people naively expected, okay, missing baryons should be plasma in intergalactic space, but there was no evidence. That was a situation before FRB. But now, you know, FRB can measure the amount of plasmas in the universe. That's direct measurement of amount of plasma, okay, using dispersion measure. So therefore, before this plasma was hard to observe using telescope, but by using FRBs, now we can measure this one, right? So I don't need to explain this again. So using dispersion measure, there's a plasma effect here. Then you measure time lag. If you have longer time lag, you have more amount of plasma. If you have short time lag, that means you have less amount of plasma in the universe. So FRB is the game changer in this missing baryon problem. So then this will give you the direct answer. Then, this is the same thing, right? So I'm just saying same thing. So you use time lag, and then you measure amount of plasma. This gives you the answer about missing barium problem. And then many people are excited because this long-lasting missing barium problem is finally resolved. People expect this, by FRBs, okay, towards resolving missing barium problem. Okay. Then this almost resolved. I would say almost resolved. Let me explain this figure. So this is from Nature paper. So not from us, but yeah, show me. So y-axis is showing the how much, if I simplify, how much amount of plasma exists in intergalactic space. Okay. And this is indicator of baryons. Okay. How much baryons you have in intergalactic space. This can be measured by using dispersion measure of FRBs. Okay. So DM means dispersion measure, not dark matter. So this is dispersion measure. So therefore, this is y-axis measured from FRBs. Okay. How much baryons we have in universe. We have direct measurement. And x-axis, this is, I hope you have heard about this one, redshift. So this is many meanings, but if I simplify, a small redshift corresponds to the nearby universe. And a large value of redshift corresponds to distant universe. This is one way to explain. Anyway, this redshift can be measured from the galaxy where FRB happened. So we can find the galaxy. Then by observing galaxies, so we can measure the redshift here. Anyway, and these data points are measurements using first radio burst. Okay? And then there is a straight line here. So this is the theoretical expectation. Theoretical expectation. This one. Theoretical prediction. Assuming that majority of the baryons in the universe, majority of the baryons in the universe, including missing baryons, they exist, if they exist in intergalactic space, then people predict this way. Okay? If majority of the baryons, including missing part, if they exist in intergalactic space, so then this prediction, it should come here. People can calculate using cosmology that you are learning, okay? And then a gray shaded region, this is a kind of expected fluctuation of amount of plasma at different locations in the universe. Say, our universe is not completely homogeneous, right? It is inhomogeneous, high density region or low density region. So depending on which direction of the universe you are looking at. So this amount of plasma or amount of baryons can fluctuate because this is cosmic average over the whole universe. So people can derive average. But depending on, say, different places in the universe, so this can fluctuate. So then, many people are surprised to see this one because observed data points are basically consistent with this prediction. So please remember, this prediction is saying majority of baryons, including missing baryons, okay, they exist in intergalactic space. And this is consistent with what is measured by FRBs. So that means FRBs is already counting all of the missing baryons. And then they are really consistent. Okay. So then also this fluctuation is, but this is an exception. But this data point is reasonably distributed within this theoretical prediction. Okay. So this, both of them are really consistent. So therefore, in terms of total amount of missing baryons, this is resolved. Again, because this missing part, so this theoretical prediction assumes that missing part should exist in intergalactic space. And then this expectation in that case. And then what FRB measure is also consistent. So that means what FRB measure already includes the missing part of baryons. So in terms of total amount of baryons in the universe, so this missing baryon problem is really resolved. I would say it's really resolved. So it was decades problem, many years, but just recently, FRB really resolved this problem in terms of total amount. Okay, then total amount is finite. Total amount, okay, total amount. Okay, this is resolved. Pie chart is okay now. Then now people started to pay attention to next key question. So if we really want to fully understand the baryons in the universe, maybe next question is where they are, or fluctuation of baryons in the universe. Say, can we find different places have different amount of baryons, say depending on direction in the universe? Do we have different amount of baryons? This is kind of predicted, right? There should be fluctuation here. But this is the next key question if you really want to understand the baryons in the universe. Okay. So then this, we want to address this question in our work. I think I have a little bit more time. And then I'm going to deal with more details about our recent paper. This is from Juin Shu. She is also another alumni of NTHU. So I think you guys are all good NTHU students. She wrote a paper. Yes, let me explain this. So you are seniors. She already graduated, but yes, she was an NTHU student too. And then, what I want to understand is, this amount of baryons may be different along different line of sight or along different directions in the universe, right? So then, there are some case study already. For example, in this paper, they found the FRB happening along the direction to galaxy cluster. Maybe here. FRB happened here, but there are many galaxies here. So that means along this FRB direction, there should be many galaxies. Many galaxies. So then naively speaking, and galaxies contains baryons, right? Naively speaking, if you have many galaxies here, then I may expect the more baryons in intergalactic space along this line of sight to this FRB. Because you find many galaxies. Probably between the space between galaxies, there are probably more baryons than other places. Then they do find it. Yes, for this particular FRB, if you compare the amount of baryons measured by FRBs with this cosmic average, okay, this theoretical line, so people can use this line. Compared to this line, along this line of sight, they confirm that there is an excess in dispersion measure, excess in amount of baryons. This is delta cosmic, dm cosmic means excess. Excess means excess from this line. For example, this line has excess, right? Excess. So you have along this FRB line of sight, and there is a more amount of baryons compared with cosmic average. Okay. They found this excess along this galaxy cluster line of sight. Okay. There are similar case studies too. Previously, people wanted to focus on high galaxy number density environments because that's interesting. For this case, they also found FRB, and then behind, along this line of sight to this FRB, they also find a galaxy cluster. And then this is also similar. They also find a galaxy cluster along this FRB site. Then both of them, they also show excess in amount of baryons measured by FRBs. They are all consistent, saying same thing. If you look at high galaxy number density environments, if you find more galaxies, the amount of baryons in intergalactic space is also high. But this is just a case study looking at only high density environments. But the universe is not like that, right? So universe is not only not only high density environments, because there should be fluctuation. So we have to include the low density and the high density environments all together with a consistent manner. Otherwise, just looking at the high density environments, we don't really get a full understanding of baryon distribution. So problem was, so this case study was limited to only high density environments. But in our work, so we try to include both low density and high density regions using a unified systematic manner. Okay. So this is a point of this study. I hope that will be better than previous analysis. If I summarize the situation, now if we find a data point above this black line, we call it excess. So you have more baryons along that line of sight compared with cosmic average. But for some cases, actually you see the data points below this line. So they have less amount of baryons along that line of sight compared to the cosmic average. Okay. So we can quantify this amount of baryons, how much they fluctuate. Okay. And then we compare this excess or deficit here with the number density of galaxies around FRB position. Okay. By doing so, we can include both high density and low density environments all together. Okay, this is a new point. And then this was done by doing, she was at NTHU, I think. And then the y-axis again, so this is how much excess or deficit we can see. I mean, in terms of amount of baryons compared to cosmic average. And the x-axis is the number density of galaxies around FRB. So if you look at the FRB position, do you see many galaxies around FRB, or you see less number of galaxies? Okay, this is kind of density environments in the galaxy, in the universe. Then, even though their number of data points are small, limited, but we found, for the first time, we found a statistically significant correlation between the amount of baryons as a function of number density of galaxies. So this is the first time that we found correlation. So that means, if I simplify everything, we can see, if we look at the high galaxy number density environments in the universe, so there are more baryons, including missing baryon, in intergalactic space. Okay, that's very simple, only something we can expect. But this is the first time to find the statistical evidence of this. So therefore, if I have time, make a conclusion for this part, she found that if we look at the high galaxy number dense environments, for example, say if it happens here, and then along this direction, in the universe, there are so many galaxies. If you look at this direction, the amount of baryons in intergalactic space is high. If you look at the universe where there are less number of galaxies here, so then the amount of baryons along this line of sight is small. So then these kind of things are kind of expected, naively speaking, but this is the first time to show the statistical evidence of this baryon distributions in the universe. Okay. I think this paper is very nice, so I really feel that the student can do very good work in Taiwan. So I'm just encouraging people, if you are interested, so you can do something like this. Okay. Then I think it's good time to take 10 minutes break. So therefore, let's take 10 minutes break, and then I will resume it after 10 minutes.